Good afternoon, everyone. Welcome to our day 3 of Faculty Development Program in recent research trends on AI level in interdisciplinary domain. Today we have Dr. Imon Mukherjee sir with us. He will be taking today's session. Now, I would like to welcome our first speaker of the day, Dr. Imon Mukherjee. He has received his PhD degree from Jadavpur University, Kolkata in July 2015. Currently, he is an assistant professor grade 1 in computer science and engineering at Indian Institute of Information Technology, Kalyani. Earlier, he was an assistant professor in the Department of Computer Science and Engineering of the Institute of Technology and Marine Engineering, now the Notia University, West Bengal. Then, from January 2012, he was associated with the Department of Science and Engineering, St. Thomas College of Engineering Technology, Kolkata, with the same designation. He has published more than 60 research papers in reputed journals and conferences. He is the principal investigator of several government-funded projects from DRDO, SERB, CRG, etc. He serves as editor and reviewer of several peer-reviewed international journals and conferences. His research mainly focuses on information security. Thank you, sir, for joining us. You may start with the session. Over to you, sir.
So, thank you. And after a heavy lunch for all of you, I do not know whether how much I can bore you in this session. Let's try. And I also was thinking that whether I should thank the organizer, what happens, yeah, or I should not thank the organizer, because we the quantum people always are in different state of mind. Sometimes we think whether we should thank, we should welcome. Sometimes we should think no, we should not thank the organizer or some other people. Actually, we have learned this from the quantum computing and machine learning. You know that means you all of you are working. Most of you are working in the machine learning domain for last many years, and quantum is not too much old as compared with machine learning, but quantum computing is becoming popular day by day, and quantum and machine learning together, that is quantum machine learning, is our future. So we are within next few years we will enter fully in this era, quantum machine learning. But why quantum? Before entering to the discussion on quantum, if I ask you, can you factorize 35? I think you will easily say, yes, 35 is 5 and 7, right? So you can easily give the answer. If I ask you, what will be the factors of 323? You may take some times, but you can easily tell 17 and 19. Now, if I ask you, can you please factorize this number, especially in polynomial time? It is difficult. It is really difficult. Especially if I give you the classical computer, any supercomputer, then also you can write the programs, then also it is very difficult, I am telling you. Similarly, if I ask what will be the time complexity, all of us I think are fully aware of. So if I ask search 99 from the list using linear search, we all of us I think are well aware about linear search, binary search, interpolation search, different searching techniques. So we can easily tell you that yes, it can be easily searched with order of n time complexity. It's very simple. Now, if I ask you, can you search with less than order of n? Then it is difficult. We have to think of how we can do it. In classical computer, it is not possible. And now you are listening my words in this FTP, but are you sure that after returning back to your home, you are fully secure about your bank? If you keep the money at your home, ED or CBI will come. If you keep the money at bank, it may be hacked. If password is hacked, you are gone. So what will you do? So these are the things really we have to think of. We have to think about the solutions. This is what the task for computer scientists or computer engineers. Finally, as I started, do you think are you existing in this world? If you think you are existing, is there anybody who are just of opposite character and are belonging to other universe? That is actually even in Indian mythology also we find that Lord Krishna with multiple Brahmas. So at that time also people knew that there are multiverse, and not only this universe, there are other similar kind of universe are existing. So now if I want to communicate with that person who are there in other universe, can I communicate even faster than the time of taken by light? Is it possible? So all these questions comes in the mind, and from where the quantum concept comes into the existence, and very popular even. And I am telling you that Indian mythology is very strong. Many things we find in our Veda or different shastras, which shows that it is correct. The distance between sun and earth, it is found in Hanuman Chalisa. If I ask you what is, you know that Arundhati is the star that is moves opposite to other compared with other direction in Saptarshi Mandal. So that is everything is written in our shastras. So we are now reinventing this during our modern science. Now the question comes, okay, fine, we understand that quantum is required, but why quantum is required? Because classical is enough. We can write many programming starting from simple addition. We can do many different programming. Actually, quantum gives the advantage in many ways. In classical, we consider only one or zero state, but which are independent to each other. That is called bits. But in quantum, we call qubits, that is also 1 and 0, but there might be in between something which are in the superposition of these two states. There might be many states rather. So based on that is what is called qubits. This is qubits. That is, I will discuss in details in the next slides, that there are different properties of quantum computing, that is called superposition, entanglement, interference, by which we can perform better as compared with classical computing. Without doing any calculation, I am telling you that for classical computing, if to generate m numbers, if m log m bits are required, in quantum computing only m, for to generate m numbers only log m qubits are required. So that is the beauty of quantum computing. So as I told that classical computer is 0 or 1, but quantum bits you may consider as superfluids that live between 0 and 1, and that can live in both 0 and 1 at the same time. That is also surprising. you may think of that this is here, this one is here, or here, or here. That is in the superposition. The superposition is the most strongest aspect of quantum computing. For superposition state, in quantum, in classical, normally we represent that this is 0, this is 1. Might be that if I consider that if this one is, up is 0 and down is 1, fine. In quantum, we consider that might be that 50% probability of it is 0 getting 0, 50% probability of that it is occurring 1, or 85% probability, this is 85% probability that is near to 0, or 15% probability to it is to be 1. So that is what is called superposition. That means the same two states are in the same at the same time, it is in the two states 0 and 1. So here we represent this using a new symbol that is called bra and ket symbol. This is ket symbol, that is called Dirac-Ket symbol. We rather than writing 0, we represent using this. This is called ket and this is called bra. Will come when it is required. What is alpha beta? I told that might be that 0 is having probability 0.8, maybe that beta the probability is 0.2, something like that. So alpha beta you may consider as a probability of occurring 0 or occurring 1. Actually, later we will tell you, or actually this probability alpha, you know that the sum of the probability is 0, so 1 always. So alpha square plus beta square always is 1 here. If alpha beta is the probability, it is not that alpha plus beta equals to 1, rather alpha square plus beta square equals to 1. Maybe that one is say 0.6 and another one is say 0.2. Now 0.6, something like that. So it will be alpha square plus beta square, always will be 1, some for some values of alpha and beta. What will happen for 2 qubit? In 2 qubit system, we use the term mathematically we denote using this symbol that is called tensor product. This is called tensor product. I have told that for this one alpha ket 0 plus beta ket 1, maybe that another qubit is gamma ket 0 plus delta ket 1. So if we consider the tensor product among these, we will get this one. Simply forget about tensor product for the time being. You may consider alpha into gamma ket 0, alpha delta ket 0 ket 1 like this. So we will get this result. So using 2 qubits, we are getting 4 states simultaneously, as I told earlier also. That is the advantage. So if I use n qubits, how many states you will find at the same time? Answer is 2 to the power n states at the same times. Classically, if we want to generate all 2 to the power n states, how many bits are required? I required n 2 to the power n. How it is coming? Because we know that number of states will be log 2 to the power n into 2 to the power n. So n 2 to the power n. That means if I need to generate 4 numbers at the same time, I need 8 bits in classical, but I need 2 qubits in quantum. That is the advantage in quantum computing. In whole world, it is called that or total number of particles are there, that is 10 to the power 90. So classically, if we want to generate this number, I need 300 into 10 to the power 90 bits, while in quantum using I need only 300 qubits. it is very powerful as compared with classical computer. Even always we try, the concept of parallel computing. Suppose I have prepared some computer. If I want to forget about everything, I want to perform the matrix multiplication. Maybe that one computer is doing or considering one row of one matrix, another column of another matrix. Using that, it can perform. And second computer is or processor is doing another row, another column. In this way, we can parallelly calculate or perform determine the matrix multiplication within a lesser time. But in quantum computer, even I am telling you that it is exponentially parallelism advantage you will be getting, and that is inherent for any quantum computer. As I told you already, that alpha square and beta square, if I say alpha ket 0 plus beta ket 1, it will be alpha square plus probability will be alpha square plus beta square equals to 1. Now, this is a very, very important property for any quantum system, that is called entanglement. That is, two qubits might be entangled and will give you that suppose 0 0, the probability is 0.25, 1 0 is probability 0.4, 0 1 probability is 0.1, or 1 1 the probability will be 25%. Now, if you want to change any direction, it will affect much, and both it will be affected like this, and both are entangled. So you cannot separate one qubit from others in general. What is entanglement? I am coming. Before that, I will show you one video. It will be clear what is entanglement. Before that, on another property I am telling you, that is called interference. Interference means that if there is wave, two waves merge each other, then it will be higher. If it is opposite, then it will be it is called destructive. You will not get that amount of magnitude. Here also it happens when if there is for constructive interference, you will find this structure. If it is destructive, you will find this one. I am showing you the video that will clear you the concept of entanglement.
Quantum mechanics shows us that reality is merely an illusion. It has been more than 100 years since we started decoding the universe at the tiniest scale. Over the years, we have discovered several intriguing phenomena in quantum physics, but the most interesting is quantum entanglement. This is such a mind-boggling reality that even Albert Einstein doubted its existence. He called it spooky action at a distance. To get an idea of how quantum entanglement works, consider this simple example. Suppose you have a pair of gloves, and you place two of them in two different boxes. After that, you shuffle the boxes and ask your friend to open one of the boxes. If he opens the box and finds a right-handed glove, then without opening the second box, you know that it contains a left-handed glove. This will remain true even if you take the second box to the moon or anywhere in the universe. That's because the two gloves were entangled entities and had a connection between them. One was right-handed and the other was left-handed. But things become spooky when you try to apply this principle to particles in the quantum realm. Particles have an intrinsic property called spin. Before you measure it, it can be in any direction. To measure the spin, first you need to specify the direction in which you wish to measure it. If you want to measure it horizontally, then the two possible outcomes will be left-handed or right-handed. If you wish to measure it vertically, then the two outcomes would be either up or down. Consider the spin of two particles. As mentioned earlier, before measurement it can point in any direction. Let's now measure the spin of one particle along the horizontal direction. Then the measured spin will be either right or left, each having a 50% chance. Even if you select the second particle for measurement, you will get the same results, 50% right and 50% left. However, if the particles are entangled just like the gloves, see what happens. If you measure the spin of the first particle and found it right, then the outcome of the second particle will be 100% left. So, the information of measurement got to the second particle the moment the first measurement was made. And here's the spooky thing. This information is transmitted instantaneously. If you make the measurement in one part of the universe, the quantum information can be sent to the entangled particle instantaneously, even in the opposite part of the cosmos. Remember, traveling at 300,000 kilometers per second, light is the fastest thing in the universe. But quantum entanglement is independent of it. So far, it was believed that quantum entanglement is purely a quantum phenomenon. However, scientists have recently observed this spooky action on a macroscopic scale. Entanglement is actually a correlation between two things. In the experiment, two teams of scientists crafted two aluminum drums of a red blood cell size. Each of these drums has roughly 1 trillion atoms. They placed them on a crystal chip and supercooled the setup to near absolute zero. Finally, they hit both the drums with microwaves. Struck by the microwaves, each drum vibrated, rising up and down by about the width of a proton. This minuscule motion was detectable as a change in the voltage of a circuit connected to the drums. When the drums are entangled, their amplitudes will be correlated. If one drum is measured to have a high amplitude, the other must have a low amplitude. The experiment was set up so meticulously that there was no way the drums could communicate with each other mechanically. The microwaves served as the intermediary that lets them talk to each other. You might be wondering what the purpose of such experiments is. As things become large, they no longer exhibit exotic quantum behavior. The goal of such investigations is to bring something big into the quantum realm. The applications range from quantum computers to problems in physics that require subatomic precision, such as the detection of dark matter or gravitational waves. But perhaps the most compelling aspect of the work, beyond any applications, is that it simply brings us closer to the true quantum nature of the world.
So I think it is clear that what is entanglement is. So, as now the question is how we can get that qubits. Qubits can be realized in different ways, like atoms, polarizations of photons, or spin of electrons, like this. Maybe that you may consider that vertically polarized photon you may consider as gate 0. You may consider that horizontally polarized photon as gate 1. Or maybe that for electron spin, if it is up spin, you may consider gate 1. Down spin, you may consider gate 0. In this way, you may think of. So, as I told, that any qubit can be represented as alpha gate 0 plus beta gate 1. That where alpha square plus beta square always will be 1. So that is the basic representation of any single qubit. This is the linear combination. If we want to consider two qubit system, obviously we can consider up means we may consider 1 1, up down means we may consider 1 0, down up means we may consider 0 1, or down down we may consider 0 0. So that is for two qubit system. I can consider that psi equals to A down down plus beta down up plus C down up down plus D up up. So this is the linear combination. That is, we can represent as 0 for our understanding, better understanding. We write A0 gate 0 0 or B gate 0 1 like this. But you should remember that here also same thing. A square plus B square plus C square plus D square always will be 1. So that the probability, sum of the probability, you know that always it will be 1. So here also it will be 1. For any now tensor product, at that time I told that it is simply multiplication, but actually it is not. Actually, what is tensor product? 2-qubit system actually get 0 0, that is represented by this one, ket 0 tensor ket 0. That means ket 0 is written as a matrix 1 0. So 1 0 tensor 1 0. That means if we multiply, it will be multiplied with this all elements. That means this one and this one. So 1 will be multiplied with 1 and 0. Then 0 will be multiplied with 1 and 0. So you will be getting this matrix 1 0 0 0. So that is your ket 0 0. Similarly, ket 0 1 means if you multiply zero tensor product 1. So 1 means 0 1. This one. If you perform 1 0, that means 0, 1 1, that means 1, then 0 0, that means 0, 0 1, that means 0. So it is ket 0 1. Similarly, ket 1 0 and ket 1 1. That means if you consider together, what is this? This is unit matrix. For n qubit system, we can represent psi as like this: summation k0 to 2 to the power n minus 1 ak k, where summation of ak square equals to 1. So this is the large. This is that is why it is called that quantum bits or qubits have the large memory capacity and have potential to develop the theory of quantum computation and new algorithms for quantum computing. Different applications are there. For example, quantum resistance encryption in cyber security. It has a huge impact in quantum cryptography. It has a huge impact. You know that even I have told you that factorization problem. You know the quantum RSA algorithm, all of you know. So RSA algorithm means it mainly based on the multiplication of two large prime numbers, n equals to p and multiplication of p and q. So if I can break the I can easily calculate the factorization somehow. That means it will be broken. So that RSA algorithm will run. That means cryptographic system will be under question. So that is why later I will discuss that is the factorization problem easily can be solved using quantum computer using source algorithm. I will come later. In finance also, huge transactions are done. So very fast transactions, so for speed up the things, quantum computer is very much useful. Healthcare, DNA structure, there are huge complex calculations are there. Logistics, so there are several applications are there. In chemistry, material science, optimization, machine learning, already I have told, supply chain management, risk modeling, blockchain, agriculture, national, everywhere quantum computer is very much useful. It is not, I am saying that it is useful. You may listen from some game changer.
What we can expect from quantum computing, and you are now so little. You have made some big breakthrough.
Now it's an extraordinarily important milestone. Last year we achieved something what's known in the field as quantum supremacy. It is when you can take quantum computers and they can do something which classical computers cannot. And I like the way you characterized it. It's as inspiring a milestone as the Deep Blue movement or AlphaGo playing with laser doll. To me, nature at a fundamental level works in a quantum way. At a subatomic level, things can exist in many different states at the same time. classical computers work in ones and zeros. So we know that's an imperfect way to simulate nature. Nature works differently. So what's exciting about quantum computing and why we are so excited about the possibilities is it'll allow us to understand the world in a deeper way. We can simulate nature better. So that means simulating molecular structures. So maybe we can discover better drugs. Understanding climate in a deeper way so that we can predict weather patterns and tackle climate change. We can design better batteries. Nitrogen fixation, which is the process by which we make the world's fertilizers, accounts for 2% of carbon emissions. And the process hasn't changed in a long time because it's very complicated. Quantum computers one day allows us the hope that we can make that process more efficient. So it's very profound. We've all been dealing in technology with the end of Moore's law. It's really revolutionized the past 40 years, but it's leveled off. So when I look at the future and say, how do we drive improvements? Quantum would be one of the tools in our arsenal by which we can keep something like Moore's law continuing to evolve. So the potential is huge, and we'll have challenges. In a 5 to 10 year time frame, quantum computing will break encryption as we know it today. But we can work around it. We need to do quantum encryption. So there are challenges, as always, with any evolving technology. But I think the combination of AI and quantum will help us tackle some of the biggest problems we see.
And you add also to a certain extent genetics. I mean, I think quantum computing and biology will one of the biggest will have.
So next 1-2 decades are totally based on quantum computing, rather quantum machine learning. So this is a history of quantum computing. That is, it started from 1980. Actually, the first quantum mechanical model of the Turing machine was proposed by Paul, the scientist Paul, in 1980. Then Richard Feynman published one paper where he has thrown one question that the computer scientist, that can you deal with the probabilistic aspect of the quantum machine in computer, because we use the digital computer machine. Here in digital system, is it possible? In 1985, the Deuce has suggested the comprehensive framework for the quantum computing. In 1986, Feynman, he introduced himself again the very early version of the quantum circuit. In 1992, Deuce and Josa proposed the first algorithm that shows that how quantum is better as compared with the classical computer. In 1994, that I was talking about, that factorization of large numbers, how it can be done. If it can be done, so that is a threat for the RSA algorithm encryption. So Peter Shor did in 1994. The Professor Grover of IIT Delhi in 1996 proposed the search algorithm in quantum computation in root n times. In 1998, Chuang and Neil, you will find a book of Chuang and Neil on quantum computing. That is good book. You can buy this book. So that they created the first 2-qubit quantum computer to perform the computation in better way, faster way. Different companies are now trying to build up, especially IBM. IBM in 2016, they have started first cloud-based quantum computing. In 2019, then 2022, they proposed that 433 qubits processor came in the market. In 2024, more than 1,000 qubits processor we are expecting it will come in the market. Google also trying. In 2021, they were successful to build the quantum device that can solve faster than a supercomputer. Other companies also parallelly are trying for developing the quantum computers. You know that our Prime Minister has announced 6,003 crores around for the research in quantum computers for National Quantum Mission. So, but the major threat for quantum computer is that the decoherence. That means it is very difficult to maintain the for any quantum system to stop the interaction between with the outside world that might leak away the information, that is called decoherence, or the noise that may comes from radiation, cosmic wave, or phone calls, heat, or other particles. So it is very challenging to create the noise free qubits, especially when the number of qubits are very large. It is very difficult. Error rates increases even if the number of qubits becomes large. Crosstalk, I am not discussing in details what is that. Connectivity, when it will be in the network, or systematic errors. If so all these are the different types of errors that occurs while building while creating the qubits or while creating the quantum computers. If you want to but before going to that level, I just today will give a smell of what is quantum gates, how the circuits can be developed, brief idea. That is for this is, suppose this is quantum aware. So if you pass ket 0 from here, you will be getting ket 0 here as output, or if you pass ket 1 here, you will be getting ket 1. If you pass a ket 0 plus b ket 1, then you will be getting a ket 0 plus b ket 1. So quantum wires is simply just passing the qubits with the same probability, nothing else. Now there are some gates. We all know that NOT gates. What NOT gates does that if it is 0, it will be converted into 1, or 1 will be converted into 0. Similarly, here also 1 and 0 will be converted into each other. So if it is A0 plus B1, then it will be A ket 0 ket 1 plus B ket 0. It is the matrix that is if it is 0, it will be 1. If it is 1, it will be 0. So that is why the matrix representation is that 0 1 1 0. So if you want to convert 0 to 1, how you can convert it? You can simply, you know that what is ket 0. Ket 0 means 0, ket 0 means 1 0. So if you multiply this one and this one, you will be getting 0 1. You can do the multiplication, you will be getting this thing. Very simple. So that is why X gate is acting as not gate. That is what you know in classical system. Similar kind of thing. This is the matrix multiplication that I was talking about. That if you multiply this one, you will be getting 0 1. This multiplication. So you will get ket 1. Similarly, X get on 1, ket 1, you will be getting ket 0. Very simple. Now what will happen if you use 2 X gate? Suppose I am passing ket 1. It will be simply ket 1. After ket 0 will be converted into ket 1. After that again it will be converted into ket 0. So ultimately X and X will nullify the effect. This is the thing. If you pass A ket 0 plus B ket 1, you will get A ket 1 plus B ket 0. Again it will be converted into A ket 0 plus B ket 1. That means same as this one. In matrix form, you can, if you multiply X matrix with X matrix, this one and this one, you will get identity matrix I. So this is the thing, that means I into ket means ket psi means psi. So there will be no effect. It is same as the simple quantum wires that I have already described. So these are the three. This gate already I have told. These three are called the polygates. This is poly X, the actual name. This is poly Y, and this is poly gate, jet gate. So actually X can be represented as this one also. What is this? All of us know that this is outer product. So if you find ket 0 means 1 0 and ket 1, this is ket 0 means 1 0 and this is bra 1. Bra 1 means this will be ket means always the column vector and bra means always the row vector. So 1 means you can write this plus ket 1, that means 0 1, and bra 0, that means 1 0. So if you find this, that you will get the same matrix, this one, this one. So if you apply X on ket 0, you will be getting ket 1. In other way, we can derive this. I can write X 0. So X means this one I have told. So if you replace X by this, then what you will get? Ket 0, then bra 1, ket 1. Bra 1, what are you saying? Yeah, if you apply X gate, you will be getting, if you multiply these two, you will be getting ket 0, bra 1 into ket 0. So bra 1 and ket 0, that means it is 0. So this term will be cancelled. Then ket 1, bra 0, ket 0. That means this gives you actually 1. If you know the inner product and outer product concept, if you have, you can easily calculate. So you will be getting, that is 1. So that means I will be getting here 1. So in this way, in the similar fashion, I can apply Y gate and I can apply the Z gate also. So there are some simulators. If we have time, we will show you that how we can use that simulators. Let's see. So if you apply 0 in the if it is ket 0, if you apply X gate, you will be getting 1, ket 1 with 100% probability. Similarly, 1, if you apply X gate, you will be getting 0 with 100% probability. If you apply Y, as I told, you will be getting I with 100 I into ket 1 with 100% probability. If you on 1, if you apply Y, it will be minus I ket 0 with 100% probability. Similarly for Z gate also, Z gate you will be getting 1 plus I ket 0 with 100% probability. For if you apply on 1, you will be getting minus 1, this is 0 I, so that means this term will be 0, here also this term 0, so ultimately ket 1, so that means it is equivalent to minus 8. Hadamard gate, this is very interesting gate. If you pass 0 here you will be getting 0 plus 1 by root. That means you will be getting superposition of 0 and 1 with equal probability. If you pass 1 here, if your qubit is 1, Hadamard gate will convert into this one. So Hadamard gate is the actual gate that can convert any qubit into the superposition form, means 0 and 1 with equal probability. This is the matrix. This is the matrix. So if you apply on 0, I have told that 0 means, get 0 means 1, 0. So if you multiply this matrix and this matrix, you will be getting if you matrix multiply this one and this one, you will be getting this one. I am showing you. H of 0, H of 1, 0. So if you multiply these two matrix as I told, you will be getting this result. This result means what? 1 by root 2, 1, 1. That can be written as 1 by root 2, 0, 1 plus 1 by root 2, 1, 0. Isn't? So that means this is 1 by root 2, this is get 1 plus 1 by root 2, this is get 0. That means 1 by root 2 get 0 plus get 1. So that means you are getting superposition of get 0 and get 1. Similarly, if you apply on 1, you will be getting the same thing. You can do using matrix or using this form. The time is very short, that is why I am not going into the details, but you can go through the book, any books you will find it. Nelson and Chuang I have already mentioned, there is one book, that is very good book. There are other books also. One important property of any quantum gate is, if it is X gate, X into X you will be getting I, Y into Y you will get I, Z into Z you will be getting I, even H into H you will be getting I. You can multiply. You can multiply 1 by root 2, 1, 1, 1 minus 1 into 1 by root 2, 1, 1, 1 minus 1. If you multiply, you will be getting what? You will be getting this. That means you will be getting this. That is equal to I. So for any gate here, any quantum gate, ultimately if you apply twice, the result will be I. In the simulator, if you use, you will get 0 Hadamard gate, you will be getting 0 and 1, 50% probability. 1 by root 2, no? 1 by root 2 square means what? Half. 50%, 50% for 0 and 1. So 1 by root 2 means what? This value. So you will be getting the probability, you will get the superposition of 0 and 1 with 50% probability. Similarly, 1 you will be getting same, just there is one minus symbol. If you apply 2 Hadamard gate, I have told that it is 2 Hadamard gate means I, this is same as I, that means 1 through I, that means same as quantum wires, that means you will be getting 1 with 100% probability. Here also, same, get 0 with 100% probability. So these are the things you may try after that. This is same. H and H means I. Then 0 will pass to x, so that will be 1, like this. You can solve all these problems. Time is very short, so I am not going into the results. So any quantum gates actually can be represented as, or will support the property of unitary matrix. What is unitary matrix? Unitary matrix means u dagger u will be equals to u dagger equals to I. What is u dagger? U dagger means u transpose conjugate, or you can write conjugate then transpose, anything, both are same. So if ABCD is your matrix, if you perform the dagger, then you will find this thing. This is the conjugate, and then you have to perform the transpose. Transpose means row and column will be swapped. So any quantum gates must satisfy the unitary property of the matrix. So if it is x, I have already told x dagger x always will be I. H dagger also will be equals to I. Similarly for y, z, whatever the gates are there, quantum gates are there, you will get the same result. Otherwise, it will not be considered as quantum gates. So unitary matrix means it preserves the length. That means if unitary matrix U is there, if it is applied on any qubit psi, the length will be same as only psi for all gate psi. There is another gate that is called swap gate. Swap gate means it will swap. So swap means what? 0 0 if you swap, it will be 0 0 0 1. If it is swapped, 1 will come here, 0 will come here. If it is 1 0, it will be 0 1. If it is 1 1, it will be 1 1. So in a matrix form, how we can do it? I have told that 0 can be represented as, you may think of like this, 1 0 0 0, right? So this is 1 0 0 0. Then next one, here it will be swapped. 0 and 1 will be swapped. That means this one and this one will be swapped. So if this one and this one swapped, so 0 1 0 0 will come here, and 0 0 1 0 will come here. So in this way, you may remember this thing. So this is the simple swap matrix, that is swap of 1 0 equals to 1 0. Clear? Now if we deal with some other 2 qubits, that means if we consider, say for C naught gate, there are 2 things. One is called control qubit, one is called target qubit. That means if this is 0, there will be nothing. If it is 1, then it will be not operation. That means suppose here is 1 and here is suppose 0. If it is 1, this 0 will be converted into the 1. Right? So here 0 0. So this one is 0. That means this 0 will not be changed. It will remain 0. This one 0, this one 1. So this 0 will remain 1. 1 will remain 1. This is 1. This is 1. That means this control bit is 1. That means, and this is 0. That means what will be the output? If it is 1, if it is 0, it will be 1. And this one will remain same 1. So this will be 1 1. That is why this is 1 1. Similarly 1 1, if this is 1, so 1, so this one will be 0. So that means it will be 1 0. Simple. So this is called C naught gate. In the same fashion, this is the matrix representation. I am not going into the details due to time. Now, one example I am showing. Suppose this is 0, this is 1. I am this is suppose this circuit. Consider this one first. 0 and y. This is y. This is x. What will be the output? This is actually when we perform the operation, we come from the reverse. That means x will come first, then y of then 0, because we are performing this operation first. Now, so this operation must be first, must perform first. So x y of y get 0. So y of get 0 means what? I of 1. Already we have seen. X of I of 1. That means I is normally value, so it will come out. So x of 1. That means what it will be? I of 0. Similarly, you can try for this one. If it is 1 instead of 0, what will happen? We will find this is the result. Okay, so this is the way I can perform the operations. If the gates are parallel, psi 1 and psi 2, what will be the psi output? Psi output will be, I will perform the tensor product between A and B, and I will perform the tensor product between the psi 1 and psi 2. We know what is tensor product, already we have discussed. So I will, as I have told, from right to left. So first I will perform A tensor product B, then psi 1 tensor product psi 2. That will be my result. So if suppose this is my circuit, this is gate 0, this is gate 1, this is Hadamard gate. What is this? Nothing. That means I, quantum wire. So how I can determine this one? H and I will perform the tensor product, followed by the tensor product between 0 and 1. Tensor product between 0 and 1. What is H? H, this is the matrix. Already we have seen 1 by root 2, 1, 1, 1 minus 1. What is 0? 0 means, sorry, what is I? I means 1, 0, 0, 1. That is I. This is my I. And 0 tensor product 1, I can write as 0, 1. You can do in matrix form also, no problem. You can write 0 as 1, 0 and then 1 as tensor product as 0, 1, and then you can perform, you will get this result. I have already discussed. Otherwise, you can directly write 0, 1 and then 0, 1 means you know this one will be 0, 1, so you can put the value. And this is the simple matrix multiplication, so you can perform the matrix multiplication. So if you, this is the matrix and this is another matrix, so if you multiply these two, you will be getting this result. What is this result? This one I can write 1 by root 2, 0, 1, 0, 0 plus 1 by root 2, 0, 0, 0, 1. So that means, what is this? This is 1 by root 2 get 0, 1, and this one get 1, 1. So that means 1 by root 2 get 1, 1. This is my result. So that is how we are getting this. So if two gates are in parallel, I can compute in this way. So similarly, another using C naught also we have. So there is a C naught gate. So same fashion, how we can compute it? I can consider one I here. So I can perform 0 tensor 0, that means 0, 0. H and I. So this is H matrix and I. And then C naught. C naught matrix is this one. So this one tensor this one, multiplication this one. So this one tensor this one means this one, with this one you will be getting this. this, if you simplify in the same fashion as we discussed in the last slide, you will be getting this. So in this way we can solve the problems. This result is very interesting because this is called actually Bell state. This is called Bell state. Why? Because we cannot represent this thing as a tensor product of any two qubits. You cannot represent as a tensor product of two matrices. This one. So that is why it is called Bell state. There are 4 Bell states. One is this. Another one is 1 by root 2 0 1 plus 1 0. This. Another one, if instead of plus if you write minus, another one this minus. These 4 are called Bell states, which are very important, especially if you want to pass one qubit from one end to another end using some, you know that we always prefer internet. So through this, if we want to pass, at that time Bell state plays a very important role. How? We will be knowing later. That one is not this today. If you have any interest, you can go through the other sources, or you may contact with me later. I will tell you. So these are the circuits that I have told you, that if it is 0, there will be nothing. So it will be 0, it will also be 0. That is why the result is get 0 0 with 100% probability. If it is 0 1, there will be no change. So it will be again 0 1. It will be 0, it will be 1. Means always get. Do not write 0 or 1 like classical computer. If it is 1, then 0 will be, this one will be 1, but this 0 will be changed to 1. So it will be 1 1. That is why it is 1 1 with 100% probability. All these are 100% probability, except Hadamard we saw that it is 50% probability. Similarly, if it is 1 0 1 1, then it will be 1 0. So this is another thing, that suppose this is 3 qubit system. This is simple wire. This is the control. This is the target qubit. So this is the C0 gate. So same. If middle one is 1, then only it will be changed. So 0 will be changed to 1. Rest will be same. Middle one 1, it will be changed. See, this one middle one is 0, so it will remains 1. There is no change. Similarly, here middle one is 0. So this one will be changed to flip to 0, will be changed to 1. So this is the thing, how by considering 3 or more qubits also. These are simulator operations. So these are the some works. I am not going into the details right now. So this is the already I have discussed this gate. I'm not going. This is very important. That is called Toffoli gate. That is actually CC0. That means control not. Means if this one 1, this one 1, then only it will be changed. So here 1 0, so there will be no change. It will be 0. It will be 0. It will be 1, same as. But this one will remain 0. But here both are 1, so it will be 1. It will be 1, but this 0 will be flipped to 1. So 1 1 1. This will be the result. So this is called CC0 or Toffoli gate. So these are some examples. I am not going to the details. So as I told, that first algorithm that shows the difference between classical and quantum deuce. So and Zeus and Joshua both are alive in the world. So we are lucky, and we are expecting something more from them. So they shows that how the quantum algorithms are better than the classical. I have already told Shor's also alive. Peter Shor, he that number I ask you. So this is the multiplication of these two prime numbers. So I am not discussing the technique because it will take another few hours only to discuss this algorithm. So, but Schwartz has shown that how we can factorize the numbers using quantum computation. Professor Grover of IIT Delhi, he has shown that how it can be done in root n searching can be done. Linear search, we know that order of n. Binary search, we know that is faster than linear search, but Grover search even better, that is root n time. So any quantum algorithms can be actually we expect to fulfill if it will be better or best algorithm if three circles are covered. What are the three circles? That is fewer number of qubits, quantum advantage, and practical utility. Till date, none of the algorithms which are available fulfill all these three. That means it is not fulfilling desired area. Quantum algorithm, it is practical utility, it has practical utility and quantum advantages, but few number of qubits, it is not possible. But IBM is trying, so I think if it is more than 1000 or 2000 qubits, it will be really threat for the cryptographers. Google quantum supremacy also is following this one and this one, but practical utility till it is not found. Till date, actually, the number of qubits in 2019 it was 27, 2020 is 65, equal 127 in 2021. This is very useful. That is already in public in 2020. This is not 2022. Actually, this came in 2023. It was expected in 22, but it did not came. 433 qubits. So these are the expectation, but not. This is we are expecting this year. Already IBM has told that they could able to reach the goal, but they have not made it public yet till date. But even if this is fine, but another thing is the number of good qubits are not enough. So actually the quantum volume, the number of all qubits does not characterize how many qubits are good qubits. So till now, if it is quantum volume is 64, that means 2 to the power 6 means 64. So 6 number of good qubits is available. So in this way, till now only 7 maximum good qubits we have got. So that is not very good. Means other qubits are noisy, mostly noisy. Okay, so I am not discussing QLOPS. Actually, QLOPS is the circuit operations per second. This is actually to measure the performance of the quantum computing. It is required. I am not going into the details. And now come to the machine learning part. I think machine learning, all of you know that whether it is cat or dog, that can be classified by any machine learning operation. So machine learning, you know that classification problem or regression problem, clustering problem, or dimensional array reduction, you know that PCA. So there are several techniques are there by which all these 4 techniques are very much useful or very much popular. All of you are, I think you have attended the FDPs from the beginning, so I think it has been already discussed in other lectures, so I am not going into the details. But these are the very important things which normally machine learning does. So quantum machine learning actually is slightly different. Slightly different means it has two things. One is data generating system and another is data processing device. So based on this, we classify this whether it is classical and quantum. So C means classical and Q means quantum. So CC means classical data generation system with quantum data processing devices. QC means quantum data generating system with classical data processing system, like this. So till now we this is all of us are we all know. QC and CQ, we are right now we are dealing with all these both the things, but we are not in at all in we have reached to this QQ system. QQ, if we reach, then we can do many things. In 2016, Kalyani and Prakash, they proposed that they proved that quantum system is quantum. They proposed the quantum recommendation system, and they have shown that it is faster, exponentially faster. But in 2018, Tang, during BTech thesis, this is very interesting. BTech during BTech thesis, and they have shown that even classical algorithm which achieve the same complexity as one of these that can be done in quantum computation also. That means he used the principles of the quantum computing in classical. So he shows that it is possible. In his PhD thesis, he dequantized the several many QML algorithms. For examples, the classical algorithms which can be inspired from the quantum principles, like quantum inspired machine learning algorithm or dequantization algorithm. So these she has done during his PhD thesis, and this thesis is available openly, so anyone can see this thesis. And another thing is that is QC algorithm. QC algorithm, or that is called machine learning quantum algorithm. So that uses the machine learning to improve the quantum system. That is, quantum machine learning can do the machine quantum error corrections, or neural network can mimic the quantum systems. So these are the things which we normally do in QC. In CQ, actually, this is very interesting, that quantum computing is used to improve the machine learning. I am not going into the description of this figure. This is the simple block diagram, but I am not going into the details because already it is 5 and I have, what is the time? 5:06. So the last one, which is our future, that is QQ algorithm, or quantum generalized machine learning. That is, both the input and output data will be quantum. That is LHC, or Sun quantum computer. That is what is the future, where the principle of the machine learning remains same as CQ case. CQ means classical quantum. Already we have described in 2 slides before. So there are different models, quantum machine learning models, like quantum neural network, quantum CNN, quantum hybrid quantum classical neural network, or quantum NLP, or quantum language models. So there are a few modes also. which are the QML models that can be used, or people are doing research on this. So if you are interested, you can go through this in details. Thank you. Any question? Am I audible? Yeah.
Yes, sir. You are completely audible. Thank you, sir, very much for this knowledgeable session on quantum machine learning. Thank you, Dr. Imon Mukherjee, sir. If any participant have any question, please raise your hand, and or you can write in your chat box.
Even in future also, if you have any question, you can send me in my mail ID imon@IIIT-Kalyani.ac.in, or you can send my mail ID in my institute website IIIT-Kalyani.ac.in. You can send me the mail.
Sir, please drop your mail ID inside the chat box.
Okay, I am writing.
Thank you, sir.
I think you have got right.
Yes, sir. It is completely visible. All the participants, you can write in. You can write if you have any query. Sir has provided his mail ID. You can write also there. Anjan Ghosh. Sir,
Yeah, hi.
Anjan Ghosh.
Hi, Mr. Imon sir.
Yes, hello. Yes.
Yeah, this is Anjan from Tata Consultancy.
I cannot hear you properly. Can you tell me once more your question?
1 minute. Can you hear me now? Can you hear me now?
Anjan sir, please repeat your question.
Yeah, can you am I audible?
Yes, yes. Now I can hear you.
Okay, yeah, thanks Imon sir for your wonderful presentations. So
Again, I cannot hear you.
Yeah, thank you Imon sir for your wonderful presentation. Hello.
Hey, yes.
Yeah,
Tell me.
actually you have told about the quantum interference in the quantum computing and also the quantum entanglement. What about quantum tunneling? How it can be used in the quantum computing?
I have heard that I have discussed quantum entanglement and interference. Then what is your question?
Quantum tunneling.
Quantum tunneling.
Yes.
Quantum tunneling, I cannot tell you right now because I do not know actually. I have to check and I have to give you the answer later.
Yeah, actually, it's a concept in the classical phenomenon by the quantum mechanics. A particle, if it goes up against a potential barrier, can cross it even its kinetic energy is smaller than the maximum of the potential.
Not hear you properly.
Yeah, I'll send you by chat.
My volume is 100%. I cannot.
Anjan sir,
Okay, yes. So
write your query inside the chat box.
you can write in the chat box, or you can send me the mail. I will give you the reply.
Okay, I will.
You can write in the chat box. I have no problem.
Okay, I will mail it.
Imon sir,
Yes.
Anjan sir actually delivered his lecture yesterday. He is one
I
of
cannot
the
hear it.
valuable speaker. Hello.
Hello.
Um,
Let me take the headphone. Just 1 minute. It is disturbing. Tayon acho? Tayon? Hello.
am I audible, Imon sir? Hello.
Just 1 minute. Today system is disturbing from the beginning of the lecture. Hello.
Hello.
Ah,
Yes.
yes, yes.
Yes.
Now,
Actually,
yeah, okay.
Anjan sir is actually valuable speaker for yesterday's lesson.
Okay.
He's very much. He's an industry person actually from TCS,
Okay.
and he have some knowledge in quantum computing as well as today's cryptography, AI, and other tools that
Okay.
what are used in the industry scenario.
Okay.
From his knowledge and perception,
Hmm.
probably he try to give a solution of this question. Uh, then, sir, Anjan sir, probably, probably you are hearing.
Yes, yes, I can hear you
Uh,
loud and
now,
clear. But
now
Imon,
you can, now you can put your question and
Yeah,
discuss
yeah.
it. You can join with us with your discussion.
hi, Imon sir. Anjan
Yes.
here.
Hi, yeah. Hello.
Yeah, very good afternoon.
Very good afternoon, and it is nice to meet with you here.
Actually, as a student of the physics, so I have some knowledge in the quantum physics.
Okay.
So you have articulated about the techniques of quantum mechanics in the quantum computing.
Hmm.
So you have touched the points like quantum interference and the quantum entanglement, right?
Hmm.
So there is another concept that is quantum tunneling. So
Okay.
is it also be used in the quantum computing?
Actually, I am from the computer science engineering background. So, quantum mechanics and quantum physics both are different things. So,
Okay.
I am not fully aware of that part. So, as you are saying that quantum tunneling is one important thing, so I will search. I will study on that. I will reply on that after that. Right at this moment, I do not know what is quantum tunneling.
Okay, no issue. Maybe there is no research on that, so
Okay.
you can have a look on it on that.
Okay, definitely, definitely. Thank you very much for giving the new terms to
Yeah,
me.
thank you.
I can enrich from here. That is very good
It's a
for
very
me.
good principle of actually the quantum mechanics.
Okay, okay, okay.
Okay, thank you, sir.
Thank you, both of you, for this wonderful topic sharing. If any other person have any query, please raise your hand. Okay, sir. I think there is no one else who have any question. And thank you for your session. Thank you very much, sir.
Thank
Now,
you, thank you.
okay, we conclude today's session. We will meet again tomorrow, sharp at 3:30. And meeting link will be provided in the WhatsApp group before the session. And I am requesting all the participants, please join before 3:30. And it is mandatory to fill up the form of attendance link. Please follow the group for any further update about the FDP. Okay, sir. Thank you.
Okay, my sincere apology once more for wasting your technical issues.
No, 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 sir.
It's okay, sir. That's also all what you're presenting. That's been nicely accepted. I think enriched our participants and give a new domain to go through. We are happy enough to find you here in this stage, even if we are going through online mode. If you have some point of time, we will get in touch to be meet with physically.
Actually, I wanted to do some hands-on second session, but actually due to lack of time, it was not possible. Hands-on session even would be more interesting, but I thought that if I could, actually I have wasted just half an hour time. That was my mistake, actually, my error from my side. Otherwise, it could be possible, might be.
Machines,
Okay, fine. What we can.
machines can disturb anyone at any moment.
Yeah.
So we have to take these occasions at every moment on your life.
Okay. Thank you.
Thank you, sir, once again to be with us with this wonderful session, and we'll conclude today. We'll meet tomorrow at sharply at 3:30. Attendees, please come and join with us at before 3:30. What ma'am has been suggested. Link will be provided accordingly. Within the chat box, we provided the attendance link. At the end, we'll give you in the WhatsApp group as well. So thank you all. Thank you, sir. Uh, have a nice day today.
Thank you. I am leaving now.
Okay, sir. Okay. Thank you.